Hello and welcome to a quick video on the contact process. Today we'll be going over a couple of things. So firstly, again, going over what the contact process actually is. However, unlike our discussion on the Haber process, where we went through the whole process and then looked at the factors affecting the yield, with the contact process, there's a couple of separate steps where we need to analyze the factors affecting the yield and reaction rate a bit separately. After we've done that, we'll look at some important socioeconomic considerations in regards to the contact process. So like with all these reactions, it's really important to know what the product is actually going to be useful for, because if you understand that and you understand the importance of the product, you can kind of justify the chemical process. So with the contact process, the main product we're making is sulfuric acid. So that's the key. It's used for a couple of things. So firstly, you can pair these two together. So it's used in the production of ethene from ethanol as a dehydrating agent. Conversely, it's also used in the production of ethanol from ethene as a catalyst. And this is in a concentrated form. So it's H2SO4 liquid. And this is in an aqueous form. So that's the key distinguisher here, AQ. So that's the key distinguisher here. Also, I'll draw up a little diagram. This is like a really rudimentary diagram. Say if I have an iron block with rust on it. So recall that rust is iron oxide of any type, right? We can actually submerge this iron block into a kind of like a tub of concentrated sulfuric acid. So the rust will kind of dissolve away, and that's a reaction that shows that here. So we have sulfuric acid with iron oxide, which is our rust. These two react to give you iron sulfate. So notice how the solid rust is now forming an aqueous compound, and it gives us water as a byproduct as well. So in this way, rust can kind of be removed from iron, and also should be stated that the actual iron block, so the Fe, so the pure Fe, does not react with sulfuric acid. So that's the main takeaway. Also, ammonium sulfate, so this compound here, NH4 to SO4, that's used highly in fertilizers, and it's really good for plant growth, encouragement of plant growth. And you can make this compound by reacting sulfuric acid and nitrogenous compounds such as ammonia. So the first part of the contact process is something that we know as the flash process, and the goal of this, or the objective of this, is to get our elemental sulfur. We're going to use this sulfur in the contact process to make sulfuric acid. So where do we get this sulfur in the first place? Because we can only use the flash process if we know that there's sulfur under the ground. Speaking of, sulfur makes underground deposits in or near hot springs or volcanic regions, and especially in a geographical location known as the Pacific Ring of Fire. It's not entirely crucial that you memorize these details, it's just good to develop some context. Now, why do we need a process to actually get the sulfur? Why can't we just mine it? It's a good question, and it comes down to sulfur's melting and boiling points. So with something such as a metal, such as iron, it has a very high melting and boiling point. So we can mine it, we can get the ore of iron or iron ore, and then we can kind of just melt away the impurities. But with sulfur, it already has a low melting and boiling point, so we can't melt away those impurities really easily. And also, due to its low melting and boiling point, it makes it really hard to mine in the first place. So we need to do some clever chemistry using those properties in order to get purified sulfur. And that's exactly what we'll do in the flash process. So the first thing we're going to do once we find this sulfur deposit is drill this piece of machinery directly into that deposit. Essentially, it has one larger pipe with 3 smaller concentric pipes within it, and each of these serve a specific function in order for us to extract that sulfur. We're going to go through each of the functions now, starting with the superheated liquid water. So this is your superheated liquid water coming through the outside. So if you can imagine, this is kind of like a cutaway of the pipe, and your superheated liquid water is on the outside, right? So the first thing we're going to do is inject or pump through water at 165 degrees Celsius. Now you might be seeing a little bit of a contradiction happening here. So I say liquid water and 165 degrees Celsius. It's a bit of a double entendre because the boiling temperature of water is 100 degrees Celsius. So how can it be liquid water at 165 degrees Celsius? This is because the water, or the superheated liquid water, is under a high pressure. So this prevents it from forming a vapor or a gas, right? So it stays a liquid even at that high temperature. Basically, what we do with this is we melt the sulfur. If we look at the melting point of sulfur, it's 113 degrees Celsius, and the boiling point is 444.6 degrees Celsius. So that temperature of 165 degrees Celsius is directly between those two. So that means sulfur is going to form a liquid at those temperatures, right? So thus, we'll leave it there. Our sulfur has melted due to the superheated liquid water, which is a liquid under high pressure. So where we're currently at is we have our liquid sulfur and we also have water at the bottom as well, because that water hasn't gone anywhere. Although it has melted the liquid sulfur, it's also just stayed in that deposit. So we have a combination of liquid sulfur and water. So these are both compounds that are relatively immiscible, because liquid sulfur is nonpolar, so it's immiscible in water. In other words, if I were to get a cup full of water and pour liquid sulfur on top of it, it would make two separate layers, right? What we do to solve this problem is we, through the middle pipe, force through a lot of compressed air, which is coming through at high velocities and high pressure, right? What this does is it makes an emulsion. So if I have two immiscible substances, for example, oil and water, and I vigorously shake them, what it will do is it will make an emulsion where one compound is evenly dispersed in another. A good example of this is like oil and water. If I mix oil and water together and allow it to settle, it forms two layers. However, if I mix it vigorously, you get an even dispersion of the oil in the water, and that's exactly what's happened. By forcing compressed air through the middle pipe, it kind of emulsifies that liquid sulfur and water, so you get an even distribution of that liquid sulfur throughout that water. So currently where we're at is we have our liquid sulfur and water emulsion sitting at the very bottom of this deposit. So if you can imagine, we've injected superheated liquid water at high pressure. We've injected compressed air at high pressure. So this emulsion has to go somewhere due to the high pressure, right? And thus as a result, due to the high pressure, it goes in through this kind of intermediate pipe here. And then that sulfur, water, and air mixture kind of leaves for purifying for use in our contact process, really. Now you might be thinking, we have sulfur, water, and air, right? A mixture of all three. Or we have an emulsion of sulfur and water. How are we going to get our elemental sulfur? So we need sulfur solid. We need elemental sulfur for use in the contact process, but currently we have an emulsion. So we need to get rid of the water somehow, right? This comes back to the low melting point for sulfur. So as you can imagine, as it's traveling up this pipe, right? It's going up towards this pipe. It's going to go from initially 165 degrees and slowly start to cool down. As it slowly starts to cool down, it's going to go beneath its melting point of 113 degrees Celsius and go from sulfur liquid to sulfur solid. Also, if we look at the properties of this sulfur solid here, it's a covalent structure that's non-polar. So it's going to have a really bad solubility in that polar water. So thus, we can really easily separate it out. And if we combine this with its density of 2.07 grams per centimeters cubed, it's going to form a solid sulfur deposit at the bottom of the water when we collect it, right? So we can have, once we collect this emulsion and we allow it to cool, we can have our water and chunks of sulfur at the very bottom, and which we can collect very easily. Also, it should be stated, I'll clear this slide, it should be stated in the way of safety. Sulfur is relatively inert, it's non-toxic and non-volatile. Sulfur in its purest form, that is, and it's safe for workers to handle with, and they don't really need any special precautions rather than your regular PPE. So we've finished with the flash process side of things, and we're starting with now the contact process side of things. So step one is the oxidation to sulfur dioxide. So with the flash process, our final product was solid elemental sulfur that was relatively pure. The first thing we're going to do is melt that to form our liquid sulfur here. So with the next step in this, we're going to get this liquid sulfur, and I'll draw a diagram here. We have a nicer diagram at the very end, but just for your understanding, I'll draw a little diagram here. So we have our sulfur liquid, and we're going to aerate this compound, so form a fine mist. And then what we're going to do is we want this sulfur liquid to react with oxygen in the air, right? So we can have air coming through. However, if we just pump through regular air at that high pressure, we'd run into a problem because regular air has a high moisture content, right? And we don't want that because that sulfur is going to react with water and give us a acidic byproducts that we don't want yet. So that's going to decrease our yield. We want as much of possible of that sulfur liquid forming sulfur dioxide. That's what we want in the contact process. We don't want any of it reacting with water that in the air. So how do we kind of solve this problem? We use dry air, which is basically air that's been dried using sulfuric acid. You don't really need to know how it's been dried, just know that it has been dried with concentrated sulfuric acid. So the net result of this is our sulfur liquid mist reacting with our dry air or oxygen in our dry air to give us sulfur dioxide, and this is an exothermic reaction with an enthalpy of minus 297 kilojoules per mole. With any reaction in this topic, we need to have a discussion or a quick discussion about maximizing the yield and the reaction rate for this reaction here. The easiest way to maximize the yield is using an excess of dry air or excess O2. So we have an excess of this compound here. You've imposed a change on a system that's otherwise in equilibrium, so thus the reaction is going to shift from left to right to counteract that change, thus increasing the yield of sulfur dioxide. Increasing the temperature will also give you an increase in reaction rate. We've covered why in a couple of other videos, and I've just written a short monologue on why here. However, an increase in temperature is going to favor the endothermic reaction because, as you can imagine, we form heat here. So thus, if you increase the temperature, you're going to increase the heat. That's a change on a system that's otherwise in equilibrium. The system's going to use some of that heat and shift from right to left, decreasing the yield. So we come at a bit of a kind of a weird situation where if we increase the temperature, we increase the reaction rate. Good. However, if we increase the temperature, we decrease the yield. So thus we kind of need a compromise, right? And our compromise is at 400 degrees Celsius. Similarly, with the pressure, if we increase the pressure, it increases the reaction rate. And we've gone over this concept a couple of times. That's a short monologue as to why, because it increases the frequency of the collisions because the gaseous molecules are kind of closer together. Also, an increase in temperature is a change on a system that's otherwise in equilibrium. In regards to Le Chatelier's principle, it's going to shift to the side with the lowest number of molecules, and that's the side that favors sulfur dioxide. So thus, an increase in pressure is going to increase both your reaction rate and increase your yield. However, high pressures are really hard to maintain. They're really costly. So thus, very similar to the Haber process, we have a compromise. So we compromise reaction rate and yield, and the ideal optimal conditions is a temperature of 400 degrees Celsius and a pressure of 150 kilopascals. So the next step in the contact process is catalytically converting this sulfur dioxide that we made in the previous step to sulfur trioxide. So this is an oxidation reaction, and the catalyst that we use is vanadium pentoxide, right? Now, we actually do this in a really interesting manner. So we have the sulfur dioxide that we made in the previous step, and this is kind of the whole apparatus. The image on the right is the whole apparatus that we're using for this reaction. So we have the sulfur dioxide that we made from the previous step, and that's being kind of pumped through this reaction vessel here. This reaction vessel has a series of catalytic beds, which if you like, is just a tray of vanadium pentoxide powder, right? So we use a powdered form of the catalyst to increase the surface area and thus increase the reaction rate. So these are all vanadium pentoxide beds. So you can kind of think of these beds systematically. So at the first bed, I have sulfur dioxide reacting with O2 to give me sulfur trioxide, right? However, we achieve a yield of 70% at this first bed, right? So 30% of the sulfur dioxide that I have is still unreacted. This kind of goes down, that sulfur dioxide will go down. And at the second bed here, it's going to react with more O2 that I'm pumping in. So at each bed, I'm pumping in more cooled O2. And you'll see the relevance of that cooled air in a second. So that's going to make some more sulfur trioxide, right? At that third bed, I'm going to have some more leftover SO2, which is going to react with more cooled air to form some more sulfur trioxide, right? And progressively, using this kind of layered bed structure or layered catalyst structure, we get a pretty high yield. Now you might see a pattern starting to develop. So at the first bed, we have 600 degrees Celsius and 150 kilopascals, and that's a yield of 70%. At the next bed, it's progressively cooler because of the cool air that we're injecting in excess, right? So also note that we're injecting air in excess. At the third bed, it's progressively cooler still. At the fourth bed, progressively cooler still, and so on and so forth. So basically, we go from 600 degrees Celsius initially to a much cooler catalytic bed, and you'll see why in the next slide. Overall, we get a reaction yield of 99.7% at the end of the reaction, and we get some pretty pure sulfur trioxide gas. We'll start with the second dot point here, the effect of the catalyst. So basically, the whole reason why we're using a catalyst is to increase the rate of reaction, right? How it does this, how a catalyst increases the rate of reaction, is by providing an alternative way for the reaction to proceed that has a lower activation energy. So thus, more molecules will have the appropriate amount of energy to kind of leapfrog that activation energy barrier. So thus, more molecules will react successfully and we'll get an increase in reaction rate. With the previous slide, we have a little error, so it should be 2 SO3 instead of 1 SO3. However, we'll continue our discussion on temperature and pressure and how they affect reaction rate and yield. This kind of mirrors this reaction in step 1, but we'll go over it individually in the way of review. An increase in temperature is going to increase the reaction rate. Firstly, we went over why in step 1. An increase in temperature is going to decrease your yield. This is because the reaction, like the one in step 1, is exothermic. An increase in pressure is going to increase your reaction rate for the same reason as the one in step 1. An increase in temperature is going to favor the side with the lowest number of molecules, which is this side here with sulfur trioxide, and thus an increase in pressure is also going to increase your yield as it did in step 1, right? However, why did we progressively cool the catalytic beds? If you go back to the slide here, our first catalytic bed was set at 600 degrees Celsius, right? We did this in order, I'll add the 2 here as well. We did this in order for the catalyst to work best, and it works best at 600 degrees Celsius. However, we progressively cooled the catalyst, so we went for 400 degrees Celsius and so on and so forth by introducing cool air. This does a couple of things. Number one, by adding excess air, we're maximizing our yield that way, number one. And number two, by progressively cooling it, at the first bed, we can make use of the catalyst fully. So the catalyst works best at 600 degrees Celsius. Progressively, as it's cooler and cooler and cooler, we can use Le Chatelier's principle to maximize our yield. And that's how we get from a 70% yield on the first bed to a 99.7% yield at the final bed. This is because as it's cooling down, it's kind of a change that you've imposed on a system that's in equilibrium at each step, right? So what it's going to do, so I have plus heat here, so this is an exothermic reaction. If I'm progressively cooling it at each step, the system is going to react in a way to minimize the impact of that change. What it's going to do is try and heat up. So it's going to shift from left to right and increase the yield. So thus, in the way of review, 600 degrees Celsius is to maximize the catalyst or the effectiveness of the catalyst. However, the yield's not that great. What we do to maximize the yield is progressively use cooler and cooler catalyst and excess oxygen, right? So thus, at the very final bit, we get a yield that's very, very good. In step 3, we have the production of oleum. So bear with me, I'll explain why we do this step in the next slide. However, sulfur trioxide is then cooled and then reacted with sulfuric acid to form a substance called oleum. So this is oleum here. Now you might be thinking, why don't we just do this? Why don't we just have water and SO3 and we make sulfuric acid this way, right? You would think that's very easy. However, this reaction has a couple of problems. Firstly, it has incredibly low yield, which is a problem on an industrial scale. Secondly, it's exothermic and generates a lot of heat. So this H2SO4 and this water would basically make a mist, which is incredibly hard to collect. So you have a reaction that's, number one, has a low yield, and number two, is difficult to collect. So on an industrial scale, it's not worth doing. So this is where the crux of using oleum comes in, and then step 4 in the final process, we convert that oleum to sulfuric acid. So we're in effect kind of using sulfuric acid to make more sulfuric acid, right? So in the diluter, the oleum is slowly dripped and reacted with water to form 98% pure sulfuric acid. So oleum is reacting with water and giving you 2 sulfuric acid molecules. So this is a nice diagram showing where and how each of the steps occur. I find it's easiest to learn from pictures, so I recommend you use this picture and just write the reactions for each of the steps and how we maximize the yield at each of the steps. If you don't want to just look at PowerPoint slides. One thing I've left out is a step 4, which happens in a diluter. So basically, this is the step where we form our oleum. So concentrated sulfuric acid reacting with the sulfur trioxide in this step, and basically we send it off to the diluter in step 4, where that oleum is slowly reacted with water to form our product, obviously, which is sulfuric acid. So hopefully you've got a pretty good understanding of the FRASH process and the contact process as a whole, and now we'll have a quick discussion on some socioeconomic issues. So the first one I want to discuss is this whole concept of acid rain. So in the FRASH process, we extract a lot of hot sulfur. So this is sulfur solid that we extract in the FRASH process. This might be independently oxidized to form toxic sulfur dioxide gas. So I know we form sulfur dioxide gas in step 1 of the contact process. However, due to some inadequacies in equipment, we might have hot sulfur being oxidized by atmospheric air to form toxic SO2. This SO2 is actually, number 1, a toxic air pollutant, so that kind of has some direct effects. Indirectly, however, it can cause a formation of acid rain. This is when the toxic SO2 is washed out, or it reacts with water in the atmosphere. So that actually forms something called acid rain. So this is the reaction happening here. So SO2, that's escaped due to sulfur being oxidized in the FRASH process, reacting with water in the atmosphere gives you an acidic compound. So these sulfur dioxides reacting with the atmospheric water creates a phenomenon that we know as acid rain, which by definition is rainwater, so literal rainwater that has a pH of below 5. It actually has a lot of bad consequences on the environment. There's a whole list that you can look up. We'll touch over a couple of common ones. So if the quantity of the acid rain is greater than the capacity of the environment to actually neutralize it and deal with it, we can get this acid rain kind of depositing on a lot of structures and causing damage. So in soil, it can make the pH drop, and it makes it difficult for plants to absorb sufficient calcium or potassium or other nutrients, so it can directly affect plants. It can also just adjust soil chemistry as a whole and cause the death of microorganisms, and cause the release of insoluble metals such as aluminium and mercury in the soil and make it toxic potentially. It can actually, as well as affecting the soil, damage plants directly. So plants actually tend to have this waxy cuticle structure. So if you can imagine, that waxy cuticle structure will obviously be damaged by this kind of acid depositing on top of it. Also, it can actually affect man-made structures. So concrete, mortar, limestone, and marble can be directly dissolved or damaged by acid rain, either or. It can also cause corrosion in iron-based structures as well. Especially a large cause of damage is amongst aquatic life. So if you can imagine, any aquatic life results in a fine balance between nutrients such as O2, CO2, and also pH. So the pH of water is really, really important to the sanctity of aquatic life. If we have acid rain depositing continuously over maybe decades or millennia, it can really impact or even stunt the growth of fish, and that'll be delirious for the environment. As well as the fact that SO2 can cause the production of acid rain, it can also it's actually a toxic pollutant. It irritates the respiratory system and can cause something like bronchiectasis for the nearby workers. So although we said that sulfur by itself was inert and safe for workers, sulfur dioxide definitely isn't. So how we get around this by forming as little sulfur dioxide as possible is by rapidly cooling the sulfur liquid that we form by the emulsion to quickly form sulfur solid, which we use in the contact process, right? However, there's a slight problem with this, and that alludes to the concept of thermal pollution. We use water in the reaction vessel. We kind of surround the reaction vessel with cool water to cool down that liquid sulfur into that solid sulfur as quickly as possible, right? However, that water, in an effect that was initially cool, gets slightly warmer, and that warm water is released into the local waterways, right? Or at least that's what used to happen. The problem with this is a phenomenon known as thermal pollution. You might think that's relatively unassuming. We're just releasing warm water into the environment. What can really go wrong? In effect, a lot of things can actually go wrong. First thing, warm water directly results in lower levels of dissolved oxygen in that water that you release it in. Yeah. Number two, that in combination with a rapid temperature change can really impact aquatic life, especially those that are really sensitive to the levels of dissolved oxygen and water. When you pair that with potentially the formation of acid rain, that can really cause, this whole process can actually cause really bad consequences for aquatic life. So in effect, how we deal with this problem of thermal pollution is by, we have the wastewater that we've used to cool the sulfur liquid to the sulfur solid. We put this in a reservoir, let it cool sufficiently over time, and once it's cooled to an appropriate temperature, we purify it and then release it into the surrounding water bodies, right? One other socioeconomic issue is that the water or the wastewater might have sulfur impurities, which can directly cause a shift in pH and ion impurities in the water, in the local water bodies that we release it to, and this can also adversely affect local ecosystems. So guys, with questions, especially with regards to socioeconomic issues, it's important that you state a couple of really big ones. So these tend to be 6, 7, 8 markers sometimes. So it's important you state some really important socioeconomic issues, and then if you want to grab those extra marks, propose a way that you can solve it. So for example, we have thermal pollution. A way we can solve it is by having a reservoir to cool the water and then releasing it into the environment, for example.